Hi, welcome to Mathematics with Tom. I am Tom, and today I'm going to introduce you to second order linear differential equations. And it all begins with a spring. And let's take a look at how this works. So I'm going to make a diagram to help us see and to track this process. So here's my diagram. It's a three-step picture, so leave yourself a little space. So here's the first step. Step one seems like a good first step. Step one is, this is like a ceiling here. And the first thing we're going to do is we're going to attach a little spring. Something like that. Okay, so draw a spring. And the spring here, let me do it this way. The spring, we'll say, is at some initial position of y of 0. Then, so let's see, step one. Or yeah, I'm going to put it up here. So 1. A spring of length y0 is attached to a ceiling. Okay, step 2. Step 2, let's do this. Now we're going to attach a weight onto that. So step 2 is attach a weight of mass m to the spring. Okay, well, let's do that. So now this is step 2. We're going to draw this out. So in step 2, we're going to attach our spring, and this time we'll make it a little spread it out a bit. Okay, and there's my mass m, and let's connect our spring there. Now let's come over here. Notice that now we're at some position y1. Okay, so the spring is this. The spring is stretched to an equilibrium length of y1. Oops, y1. Okay, now here's where the problem gets interesting. At equilibrium, the two forces, I'm going to rewrite this. So now we have two forces at play. Two forces, because I already said equilibrium, there's no need to say that again. So two forces at play. Gravity pulls on the weight by the force m times g, where g is the gravitational constant. G is gravitational constant. Okay, now here's the other part of the picture. So we have gravity is pulling it down, but the spring stops. It comes to rest. It doesn't just keep pulling down. That means there's another force that's pulling back up. That is Hooke's law. So Hooke's law says the force of the spring, is proportional to the length of the stretch. Length of the stretch. And we're going to, traditionally the letter K is used to represent that, and it's also, and K is just a positive number, so we're just going to write K as some positive number. Well, those two forces are equal, so this gives us this. So thus, force down equals force up. Okay, and so in other words, we can say the force down, well, that's m times g, is equal to the force being pulled in the other direction, which is k times y1. Okay? Or another way is if you wanted to say, well, the force, another way of writing this that might account for direction also is that you could think of the force going down as being, you could work it negative or positive, it doesn't matter. But say the force pulling up, or I said force down, is minus, so m times g. And then the force pulling up, that's k times y1. Well, that force, those two forces are equal, so this has to be 0. So we can write it that way as well. All right, that brings us to the third step, and probably the most exciting step. That is the one that any kid would immediately come to, and that is pull on the spring. So let's do that. Let's pull on the spring. So here we go. Stretch the spring. I'm going to scoop my writing over here so I have space. Let's see. Stretch the spring. Stretch the spring. Stretch the spring, we'll call it some distance, some length. I could use distance, but we'll call it some length y. Okay, and y is going to be a function of ty or y of t, because now we're going to create some kind of a motion that we can track when the spring reacts to being let go. Now, here's where the problem gets more interesting, and that is Newton's second law. Newton's second law says that the total force in the system I'll write it this way. Total force of the system, F, we'll call it total, is equal to the mass times acceleration. Well, now we've talked about the distance being stretched as a function of y, so we could also say that the acceleration can be written as m times the second derivative of y. Okay, well, here we go. So now we can write this equation. So let's stretch the spring, and I think it'll become more visible this way, easier to see. So I'm going to stretch my spring. So, hold on. Pretty good, healthy stretch. Now, obviously, you can't overstretch these, otherwise K doesn't hold. So there's a limit to the application of Hooke's law. But in a general use, it just models it just right. We're assuming it's frictionless, so the spring will just keep springing. Here's our mass. And we've stretched this spring now to this distance here, y. Well, this distance is obviously going to change as soon as we let go of our spring. So let's think about this. So our total force down, force down, or the total force, is, since we're using down as a minus, is equal to minus my double prime. And now think about the force up, the opposite, the force pulling back against you. As you pull on the spring, there's another force pulling this way. So the total, the net force pulling up, well, the net force pulling up is the spring. So we've got two. The net force pulling up is, well, two parts. One, as we said, there's gravity that's already pulling the spring down to its equilibrium. So that's a minus mg. Plus, but then now look at what we also have. We also have Hooke's law that's been, we pulled the spring at rest. Now we've pulled it even further. So now we can say that the length of the spring is k times y1 plus y, and that's y of t, or y of t, right then. So here we go. Actually, we'll just assume that is. I've made that clear now. Okay, but those are equal. Those are the same forces. So I'm going to come over here just below my diagram. I have just enough room. So we could say this. We could say the force down is equal to the force up. Well, the force down is minus m times g. The force being pulled up, is minus, minus my double prime. And that's equal to minus mg plus k times y1 plus y. I'm going to distribute the k's. And so what do I have? I have minus m y double prime equals minus mg plus k times y1 plus k times y. Oh, wow, that looks complicated initially. Until you look back, and let's look back maybe with this nice pretty yellow color, and let's look back to this box right here. What does this box tell us? Well, it tells us that minus mg plus k times y1 is 0. And with that information, we can write this as minus m y double prime is equal to k times y. And then we normally make our leading coefficient a positive. So write this as multiply both sides by -1. I have m y double prime equals equals minus k times y. And our final form is this, that m times y double prime plus k times y equals 0. And there we have m y double prime plus k times y equals 0. And that is our most simple second order linear ordinary differential equation. And from here we'll begin our exploration of what it's telling us. I hope that helps, and thanks for watching.